All right, this is the solution for quiz 5, physics 201, fall of 2013. This was the in-class portion of the quiz. You can find a separate video for the take-home portion. Consider this graphical representation of simple harmonic motion. When a particle is at point A, its velocity and acceleration are which of these? All right, well, first of all, its velocity is the slope of this graph. That has a positive slope, so it is a positive velocity. And we also know that the velocity is decreasing. Notice here the velocity is 0, so this slope is decreasing as it increases in time here. So since the speed is decreasing, speed is going down, that means I have an acceleration that is opposite the direction of the velocity, so it's a negative acceleration. So the velocity is a positive and the acceleration is negative, that's C. How are frequency and angular frequency related? Well, the angular frequency is equal to 2 pi times the frequency. So if I increase my angular frequency, I increase my frequency. They are linearly proportional. So that is C for number 2. Which of these has the larger angular frequency? Or you could ask the question, which has the larger frequency? And that would be the same. That's going to be B. Remember, frequency is the number of oscillations per unit time. I'll have more oscillations per unit time for object B. Ice skater spins at 2.5 revolutions where their arms are extended. He draws his arms in and spins at 6 revolutions. By what factor does the moment of inertia change in the process? All right, so I can say that I initial omega initial equals I final omega final. And I have these values. So initially it's 2.5. This is omega. And then in the final state, it is 6 revolutions per second. So my omega has gone up. That means that my moment of inertia has gone down, all right, because my omega has increased. So I can get rid of a couple of these. Let's get rid of those two. And I also know that it's going to be by this factor 2.5 over 6. So I'm just going to take the product of this 2.5 over 6, and I get 0.42. And that's going to be the answer. C is 0.42. Figure skater with her arms initially extended starts spinning at 3 radians per second. She pulls her arms in and close to her body, which is the following results. All right, well, by pulling her arms in, it decreases her moment of inertia and increases her rotation rate. So the only one of these that's appropriate is B. Her angular momentum will stay the same, and she will not have a smaller rotational rate. She'll have a higher rotational rate. All right, a flywheel in a power plant has a mass of 1,000 kilograms and a radius of 3 meters. I'm just going to go ahead and calculate the moment of inertia for these. The moment of inertia for the flywheel is a disk or a cylinder. That's 1/2 mr squared. That's 1/2 of 1,000 times 3 squared. That's 4,500. And then for the bar, or it's like a thin rod, is 1/12 mv squared. You can find these equations on your equation sheet, which is online. That's going to be 1/12 of the mass. Let's see, what was the mass? 100 kilograms and 4 meters long. Uh, 50 times 16. Or excuse me, a 12th of 100 times 16. That's going to be 133 kilogram meter squared. All right. A number of you had a mistake here. Instead of doing 1/2 mr squared, you just did mr squared. I just took off a couple of points if that was the case. All right, so now we want to apply the conservation of angular momentum. That just says that the initial angular momentum equals the final angular momentum, Li equals Lf. That is that I initial times omega initial equals I final times omega final. But in the initial state, in fact, in both states, we have 2 things contributing to this. So it's going to be I initial, or I rather, for the bar times omega initial for the bar plus I for the flywheel times omega initial for the flywheel. And then that's going to equal, they're going to come together. So this is like a perfectly inelastic collision when we're doing linear momentum. They're going to come together and spin at the same rate. So their moments of inertia are just going to combine. So that's going to be I for the bar plus I for the flywheel times omega final. And omega final is our only unknown in this equation, so let's just put in our quantities. Let's see, this is 133. Omega initial for the bar is 20 revolutions per second in the counterclockwise direction. So that's going to be plus 20 plus I for the flywheel, which is 4,500, times the omega for the flywheel is 10 revolutions per second in the clockwise. So that's minus 10. And that's going to equal to 4633. That's the sum of the two moments of inertia times omega final. And then we just solve for omega final. And omega final comes out to be negative 9.1 revolutions per second. And because it's negative, it's clockwise. Write an expression for the position of simple harmonic motion of a mass of 10 kilograms on a spring with a spring constant of 50 newtons per meter. Maximum position is 2 meters, occurs at 2 seconds. Well, let's first just write down everything that we know. So my K is given, it's 50 newtons per meter. The mass is 10 kilograms. I know that X max is going to be 2 meters, and that occurs at t equal 2 seconds. See, I think that's all that I know. Yeah, so first I just want to write the expression for the position. I know it's going to be in the form of x equals a cosine of omega t plus phi. That's the solution to that second order differential equation that we looked at in class, which comes about just equating Hooke's law to Newton's second law and solving that. I want to know what a, omega, and phi are. So a is just given right out. A is equal to the maximum displacement, which is 2 meters. Now we need to find omega. Omega for a spring is the square root of k over m. It's fairly simple to get. The square root of 50 over 10. Square root of 5, which is 2.2. And that's in seconds to the minus 1. And now I want to know phi. Now, I have this information, which I can use to find the phase shift. I know that x is equal to 2 meters at that time of 2 seconds. So I just say 2 meters equals a, which is also 2 meters. That's the maximum displacement, times omega t plus phi. Cosine of omega t. Omega was 2.2. T here, we know that it's at 2 seconds. All right, so I have a position of 2 meters at a time of 2 seconds. This is my maximum amplitude plus phi. And now I just solve this. So these cancel out, give me 1 on this side. So I get the inverse cosine of 1 is equal to 4.4 plus phi. The inverse cosine of 1, of course, is 0, so phi is equal to negative 4.4. There were some other ways to do this, but this was probably the most straightforward. So finding 4.4, negative 4.4 is our phi. So our position function then is x equals 2 meters cosine of 2.2 times t minus 4.4. So that was the phase shift described there. And let's see, that was part A. Part B is I need to know the period. Well, I already know what omega is. Omega is equal to 2.2 seconds to the minus 1. I know that omega equals 2 pi f. Omega is also equal to 2 pi 1 over the period. So the period is 2 pi over omega. It's 2 pi over 2.2. And that gives me a period of 2.9 seconds. Now, what is the initial position of the mass at t equals 0 seconds? Well, I just take my position function and plug in t equals 0, simple as that. So I just say x equals 2 meters cosine of 0 minus 4.4. And putting that in, being careful that I have it in radian mode, I get negative 0.6 meters. So that's my initial position at t equals 0. And then in the final part, I just wanted to sketch the graph. So if I have the position, the time, I know that my initial is going to be right about here at negative 0.6. Right? And then I know at 2 seconds that it's at 2 meters. So I'm going between those 2 points. Actually, let's see, it's going to be sort of more straight there. I want something like this. All right. I was just looking for a sketch. So I also wanted you to show that this is the period, and this is the amplitude, A. All right, one more. 1,000-gram mass is attached to a spring with a constant of 2 newtons per meter and set in oscillation with amplitude at 10 centimeters. I want you to find a number of these things. So it's pretty straightforward. My mass is 1 kilogram. My spring constant is 2 newtons per meter. My amplitude was 10 centimeters or 0.1 meter. And I want to know a number of things. So first I want to know the frequency. As we did before, I can find the angular frequency, which is square root of k over m. And that's going to be the square root of 2 over 1, or root 2, 1.4. And then I also know that omega equals 2 pi f. So f is equal to omega over 2 pi. That's 1.4 over 2 pi, which is 0.23 hertz. This is a small thing, but a number of you had this error, and I counted off a point for this. You were very kind of clumsy with your order of operations. Not everybody, but more than 2 or 3, where you did in your calculator you did anyways, sorry about that, but in your calculator you did 1.4 divided by 2, but then you multiplied this times pi, and that's not appropriate. That's not the appropriate order of operations. You need to be careful that you put parentheses around that denominator. So I just mentioned that because several people had that error. All right, let's see, B, I wanted to know the period. That's simple enough. T is just 1 over the frequency. That's 1 over 0.23, just 4.4 seconds. And C, I wanted to know the maximum velocity, or Vmax. We get Vmax from the first derivative of that position function, so it's equal to A omega. We know A, we know omega now. It's 0.1 times root 2, which is 0.14 meters per second. In part D, we wanted to know the maximum force in the spring. Easiest way to do this was to find the maximum acceleration. That's A omega squared, which is because the maximum acceleration occurs when the spring is fully extended. All right, so we find the maximum acceleration. That's going to be 0.1 times root 2 squared, which is 0.2 meters per second squared, and then we find the force from Newton's second law. The mass was 1 kilogram times 0.2, so it's 0.2 newtons was the maximum force. And then finally, part E, wanted to know omega. Let's see, I think I've already found omega, right? Yeah, it's root 2. So it's square root of k over m, which is root 2. And that's the end for this. Let's go into multiple choice answers.